This video, let us learn number system chapter 1 and let us solve some portion of exercise 1.1. Before we jump right into solving the exercise, let me tell you three very important things that you need to know before you solve the exercise. The first is you need to know what is Euclid's division lemma, and I will suggest you learn the statement as well. The second is you need to know what is Euclid's division algorithm, and the third is you need to know how to express algebra in their general form. I will be talking about these three things in detail before we solve the exercise, and trust me, if you know these three things very well, then understanding exercise 1.1 and solving the questions will be very easy for you. Let us first see what is Euclid's division lemma. The statement says, for any two integers a and b where a is greater than b, there exist unique integers q and r such that a equals p times q plus r, and the condition is the remainder should be greater than or equal to 0, and it should be less than the divisor. What does A, B, Q, and R stands for in the statement given above? So A is the dividend, B will be the divisor, Q will be the quotient, and R will be the remainder. This is whenever we are talking about dividing any number by a number. Now, I would like to point out three important things from the statement. The first is A should be greater than B. That means the number that you will be considering dividend should be the greater number. The second thing is the expression where it says dividend is equal to PQ plus R. And the third thing is the condition that is mentioned, that is the remainder should be greater than or equal to 0, but it should be less than the divisor. I would like to break down the third pointer into the first. The remainder can be greater than 0, but it should be less than the divisor. And the second condition, it can be equal to 0, but it should be less than b. Let us take two examples. I'll take 13 and 3, and over here 14 and 7. 13 being the greater number, it will be the dividend, 3 will be the divisor, our quotient will be 4, the remainder will be 1, and in this case 14 will be the dividend, 7 will be the divisor, 2 will be the quotient, and 0 will be the remainder. Now let's see if this division process satisfies the condition above. Our remainder is 1. This is greater than 0, and this is less than 3. That is, if I express in general form, this satisfies the first condition. Now coming to the second example that we have taken over here, our remainder is 0 is equal to 0, and this is less than 7, which is our dividend. If we express in general form, this satisfy the second condition mentioned above. Combining these two uh, condition, the examples that we have taken satisfy the condition that is mentioned in Euclid's division lemma. Now, what is the use of this lemma? Before I come to that, let us first learn what this lemma means. So basically, lemma is a helping theorem. Lemma means a helping theorem to prove another theorem or to prove another important result. In this case, that important result will be our Euclid's division algorithm. So what is this Euclid's division algorithm? Basically, this is a step-by-step process to find the HCF of any two given numbers. If we want to find the HCF of any two given numbers, then we will be using Euclid's division algorithm, and we will use Euclid's division lemma to help prove Euclid's division algorithm. That is to find the HCF of any two given numbers. So the first step is we have to divide the bigger number by the smaller number. Let's consider an example, let's say 11 and 35. So the first step is we have to divide the bigger number by smaller number, and 11 times 3 will give us 33. The remainder is 2. If we want to find the HCF, the algorithm says we should not stop here. Now that the remainder is 2, we will consider this remainder as our new divisor, and we will consider our old divisor as our new quotient. We will continue this process until our remainder becomes 0. So 2 times 5 is 10, our remainder is 1, and as I have said, we will consider 2 as our new dividend and 1 as our new divisor, and we know that 1 times 2 is 2, and finally our remainder is 0. The algorithm says stop the process when the remainder becomes 0. Then the HCF is the last divisor, which is 1 here. We will be using this in solving questions, so we will understand how to use this algorithm better when we are solving the question. The third thing that I mentioned in the beginning of the video is how to express algebra in their general form. In general form or integer in their general form. So we know that if we want to draw out integers in number line, then this is how our integer will look like, and the line goes on. So there, like if we consider 1, 2, 3, they are consecutive integer. And so let's first talk about here. We will talk about integer. We will talk about even integer, and here we will talk about consecutive even integer, and lastly we will talk about odd integer and consecutive odd integer. Let's just take example 1, 2, 3. These are integer. So what is a general form to express any integer? If we consider this as n, then the next consecutive integer, which is 2, can be expressed as n plus 1. And 3, we can express 3 as n plus 2. So if we want to express any 3 consecutive integer, remember the general form n plus 1, n plus 2. This is the general form for integer, consecutive integer. What about even number? 0, 2, 4, 6. These are even integer. And how do we express even integer? We express even integer as 2n. And if we want to express 2 consecutive integer, then 2n plus 2. If we want to express 3 consecutive even integer, we will use 2n plus 4. So please remember this. This is for even consecutive integer. This. And for odd, how do we express any odd integer? We will express any odd integer as 2n plus 1. This is for odd. How about for 3 consecutive odd integer? So 2n plus 1, 2n plus 3, 2n plus 5. This is the general form for expressing any 3 consecutive odd integer. We know that odd integer are integers like 1, 3, 5, 7, the list goes on. We can also count in the negative integer. These are odd integers. So if twice n plus 1 is 1, then twice n 3 we can express them as 2n plus 1. This is 1 plus 2. This is 1 plus 2, which is 3. This would be 3, and this is our 5. How? Let me break it down for you. So we know that 2n plus 1 is our 1, or this can be like, if we can also consider this as 5, but the next integer like would be 2n plus 3, 2n plus 5. This is a general form for odd integer. So I would like you to remember this 3 general form. This is for integer. We will be using these whenever the question mentions consecutive integer or just integer. And we will be considered this general form when the question mentions consecutive even integer, and this general form for consecutive odd integer. So those are the three things that you need to know before you jump into the exercise. Now let us begin with exercise 1.1. The first question says, using Euclid's algorithm, find the HCF of 1240 and 1984. So first let us identify which is the crater number. Here the crater number is 1984, so we will consider it as A, and our B will be 1240, which is a smaller number. Now on the side of your worksheet, on the right side of your worksheet, you can show the division, the Euclid's division, and you will express the division on the main worksheet. The expression in the expression A is equal to PQ plus R. Okay, let's start. Let us divide 1984 by 1240. So 1240 times 2 will be bigger than 1984, so we cannot consider that. We will consider times 1, 1240, the remainder will be 447. This is our remainder. Let me write this smaller. 1984 divided by 1240, 1240, 744, and then we will consider 1240 as our new divisor, times 1 again, 744. The remainder will be 694. Then consider 744 again as our new dividend. This will be again 1496, and the remainder will be 842, 496, 496. Then the last okay, as we can see over here, 248 can exactly divide 496. 248 times 2 gives 496. That is, our remainder has reduced to 0. So we will stop the division process here, and this will be our HCF. But we need to express these on our main worksheet over here. So how are we going to write? 1984 is equal to, what is our first divisor? The first divisor is 1240. What is the first quotient? The first quotient is 1. What is the first remainder? 744. Now this 1240 becomes our new dividend. So this is a new dividend, and this becomes our divisor. Basically, this will come over here and this will come over here. 744. What is the quotient? 1. What was the remainder? 496. Okay, now let's move on. 496. 744 becomes our new dividend. 496 becomes our new divisor. Our new quotient 1, and the new remainder is 248. Let me continue this on the next page. Our new dividend will be 496, and our new divisor will be 248. And what was our last quotient? That is 2, and here the remainder becomes 0. And our last divisor, that is our HCF. So Euclid's division algorithm says that our last divisor will be our HCF. So this is question number 1. Let us solve Roman number 4, 10005 and 9269. So 1005 being the bigger number, this will be our dividend, the first dividend, and 9269 will be our first divisor. 9269 times 1, we will get 6 and 5, 3, 7 as a remainder. Then we will move on to 9269. We'll take it as our new dividend. 7346. 1736 0 8 1 9 2 will be 12, 2 times 3 is 6, 7, 2 times 7, 14, 15. Our remainder will be 7, 3, 4. Okay, let me move this a little bit. Then we will consider 736 as our new dividend, and 437 times 1, 437, 992, 437, 299 times 1. I hope you can see the portion in the corner. So 299, the remainder will be 831. I'll continue over here. 138, then 299 will be our new dividend. 138 times 2, it will be 6, 7 and 2. Our remainder will be 23. Then 138 will be our new dividend, and we know that 23 times 6 is 138. Here our process has come to end since we have got 0 as the remainder. Now what is left is to express this in this form: A is equal to PQ plus R. So our first A is 10005 equals 9269 into 1 plus 736. 9269 equals 736 times 12 plus 1 plus 437. 736 is equals 437 times 1 plus 299. 437 equals 299 into 1 plus 138. 299 equals 138 into 2 plus 23, and 138 equals 23 into 6 plus 0. Finally, our remainder is 0, so The algorithm says that the last divisor will be our HCF. I hope that you have understood how to find the HCF of any two given numbers using Euclid's division algorithm. Please try to remain in question on your own. And if you have any problem solving the remaining question, then you can leave your question in the comment box below. I will surely be addressing them in my next video. Now let us move on to question number 2, that is show that the product of two consecutive integers is divisible by 2. I would like to remind you to read the question very clear and read the question slowly. Check for any keywords mentioned in the question, as here it mentioned two consecutive integer. We do not see odd mentioned here. We do not see even integer mentioned here. It just said two consecutive integer. So that means we will be using the general form n plus 1, and since it's at 2, we'll be using this. If it mentioned 3, then you will have to use this, but since it just mentioned two consecutive integer, we will just consider n and n plus 1. Let's start with the solution. Let the two consecutive integers be n and n plus 1. It is very important to introduce any general form that you have used, that you will be using in the answer in the first line. So we have introduced our general form in the first line. Now, what does the question say? The question say that we show that the product of two consecutive integer. That means we have to show that the product of these two integer will be divisible by 2. So this is the product. The product is equal to n times n plus 1. This is the product, and we know that in any two consecutive integer, 1 will always be even. Example, 1, 2, 3, 4, 5. Let us take this example. And any two consecutive integer, let us consider these 4 and 5. If we consider 4 and 5, then 4 is even. We can see that 4 is even, and 4 and 5, they are consecutive integer, and 4 is even. If we consider 3 and 4, again they are consecutive integer, and 4 is even. If we consider 2 and 3, 2 is even again. If we consider 99 and 100, this is also consecutive integer. Again, 100 is even. If we consider 999 and 1000 comes right after 999, that means they're consecutive integer. Again, 1000 is even. So what we can conclude from here is that among n among n and n plus 1, 1 will one number will always be even. I hope you can agree with this statement, that one number will always be even. I have shown you with example. So that means their product n plus 1 will always be even. And to prove my statement over here, let me explain you with some example. Consider 3. The next number is 4. 4 is even. If you multiply 3 and 4, you will get 12. Consider 1 and 2. The product will be 2, which is even. Consider 7 and 8. These are two consecutive integer. The product is 7 times 8 is 56, which is also an even number. So what we can say from here, what we can infer from this example is that any number, be it odd number, be it even number, if it is multiplied by even number, then the product will always be even number. So I hope you understand this line, that if we multiply any two consecutive integer, the product, this is the expression for the product of two consecutive integer, this will always be even. So any even number is divisible by 2. We know that 0 is an even number, and we can divide this by 2. 2 is an even number, we can divide this by 2. Minus 4 is an even number, we can divide this by 2. So any even number is divisible by 2. Therefore, let's use hence the product n plus n and n plus 1 is divisible by 2. So how do we start the question? First, we consider any two consecutive integers, and as I have told you, the general form for a consecutive integer, we have used n and n plus 1. Since the question just mentioned two consecutive integer, we have just taken two general form for consecutive integer, which is n and n plus 1. Then we express the product n plus 1, and we mentioned that among n and n plus 1, one number will always be even. I have shown you with example. Then we also mentioned the statement n plus 1 will always be even. The product will always be even. I have also supported the statement using some example. Then we conclude that the product is always divisible by 2, because any number, be it odd number or even number, even integer or odd integer, if it is multiplied by 2, then the product will always be divisible by 2. That is how we have proved question number 2. Now let us move on to question number 3. Show that the product of two consecutive even integer is divisible by 8. So the key word is two consecutive even integer. Remember I told you the general form for even integer is 2n, and it said 2 consecutive even integers. So 2n and 2n plus 2 will be our general form for this question. And another keyword in the question is product. So let us express these two general form and product form. So the product is 2n and 2n plus 2. This is the product. Now let us take out 2 common from here, 2n, and if we take out 2 as common, then inside the bracket it will be 2n plus n plus 1. Now let us group 2 and 2. If we multiply 2 and 2, it will give us 4 n plus 1. So the expression here, this expression n plus 1, I have just proved this in question number 2. This is always divisible by 2. But let us mention again in this for this question again, among n and n plus 1, 1 is always an even number. So the product is equal to 4 into even number. And then so what are even number? What are even number? If you consider 0, then this product statement would be 4 into 0. 4 into 0, which is 0, and this is divisible by 8. If you consider 2 as an even number over here, then this will be 8. This is divisible by 8. And if you consider the next even 0, 2, 4, 16, this is divisible by 8. The list will go on. If you multiply 4 and any even number, then that product will always be divisible by 8. So I hope you have understand the example. So our last concluding statement will be this is divisible by 8. That is 2n plus 2 is divisible by 8. Moving on to question number 4, let us see what is the question number 4 asking to prove or show. Show that every integer is of the form 4q plus 1, 4q plus 2, or 4q minus 1. So we want to express every integer in the form of 4q. That means in terms of number 4. We must divide each integer by 4, and we must see what kinds of remainder can occur. Let us continue with the solution. Let us take a be any integer, because we have to show that every integer is divisible by can be can be written in the form of this expression. So let a be any integer, and let's take b equals to 4. Let us use Euclid's division lemma then. By Euclid's division lemma, a is equal to, our divisor is 4, the quotient and the remainder. So since 4 is our divisor, from here we can conclude that the remainder should be greater than or equal to 0, but it should always be less than 4. This is what we can conclude. So possible values of r can be 0, right? It can be 1, it can be 2, it can be 3, but it cannot be 4 because it has to be less than 4. So we will stop here. Let me repeat that again. The value of r can be 0 because the condition says it can be 0, it can be equal to 0, and it can be greater than 0, so greater than 0, 1, 2, 3, but it should be less than 4. So these are the possible values of r. So possible values of r is 1, 0, 1, 2, and 3. Now if we substitute the value of r in this expression, we will get the values of a. So first let us substitute 0 as r, then our a will be 4q plus, instead of r, substitute it as 0, that means 4q. And then like that, let us substitute the value of r, 1, 2, 3, and if r is equal to 1, then the value of a will be 4q plus 1. If r is equal to 2, our a will become 4q plus 2, and if r is equal to 3, then the value of a will be 4q plus 3. So we will stop the substitution process here. Now let's read the question once again in the form of 4q. We have expressed in the form of 4q. Next is 4q plus 1. We have done that. 4q plus 2. We have done that as well. Here it is 4q minus 1. But over here, when we substitute the value of r as 3, this is the expression that we got. But we have to express this as 4q minus 1. So if I write here 4q plus 4, then and subtract 1, then this is basically 3. This is the same expression. I am just using subtraction operation, and so that I will be getting minus 1. I want to get minus 1 over here. So I can take out 4 as common, q plus 1 minus 1. I can just write this as 4q minus 1. So we have expressed every integer in the form 4q plus 1, 4q plus 2, or 4q minus 1. In the conclusion, you can mention hence every integer is of the form 4q, 4q plus 1, 4q plus 2, 4q minus 1. I hope question number 4 is clear. Let us take a review again how we have solved the question. The question says every integer. So we have considered A, any integer, and we have taken B, the divisor, as 4 because we need to express every integer in terms of 4 because the question asks for the form 4q, 4q plus 1, 4q plus 2, 4q minus 1. And then we have used Euclid's division lemma, and then this is the expression after using the lemma. Then we make out what is the possible values of the remainder that we can use, and the condition says that it should be less than 4. So the possible values of r is 0, 1, 2, and 3, and we have substituted the values of r for each values of r in the Euclid's division expression. And for these we have just we have tried to express 3 as 4 minus 1 because we want the expression minus 1. And that's how we have solved question number 4. Now let's move on to question number 5. Show that the product of 3 consecutive integers is divisible by 6. What are the keywords here? The keywords is 3 consecutive integer and 6. So for this question, it is 3 consecutive integer. So and we will consider n plus 1 and n plus 2 as our 3 consecutive integer. Then we have to show that their product is divisible by 6. Let the 3 consecutive integer be n plus 1, n plus 2. Their product is equal to n whole n plus 1 whole n plus 2. This is the product. We must show that this product is divisible by 6. Now if we look at 6, then 6 is a product of 2 and 3. So that means if we can show that this expression, this product, is divisible by both 2 and 3, then it is divisible by 6. So that is what we are going for. That means to be divisible by 6, the product must be divisible by both 2 and 3. Now let us just first check for divisibility by 2. Divisibility by 2. Let us first check for this. And among, let's mention this as well, among any 3 consecutive integers, 1 is always an even number. I hope you can agree with the statement. If you consider any 3 consecutive integer, example 3, 4, 5, here 4 is even. Likewise, if you take any 3 consecutive integer, 1 will always be even. So that means the product will always be even number. So an even number is divisible by 2, so that means the product will be divisible by 2. Since the product and n plus 1, n plus 2 contains an even number, it is divisible by 2. Divisible by 2. We have proof for the divisibility of 2. Now let us check for divisibility by 3. Among any 3 consecutive integers, 1 is always a multiple. One is always a multiple of 3. To support the statement, let us give example 3, 4, 5. Here 3 is a multiple of 3. And 7, 8, 9. 9 is a multiple of 3. Likewise, for any 3 consecutive integer, 1 is always a multiple of 3. So in n plus 1, n plus 2, 1 of them is divisible by 3 always. Therefore, the product is divisible by 3. Now let's combine both of them, since the product is divisible by both 2 and 3. It will be divisible by 6. Hence n plus 1, n plus 2 is divisible by 6. So we have solved till question number 5. I will suggest you to remember the statement, Euclid's division lemma, and also to remember the general form of expressing integer. You have to read the question properly, identify whether it is just asking for any consecutive integer or consecutive odd integer or consecutive even integer. And you also have to be very careful um, with the number that is mentioned in the question. In some question it asks for 3, while in some question it asks for just 2. In some question show that every integer you have to be very thorough with reading the question. And we will stop here for today, and if you have any question, feel free to leave them in the comment box, and please do consider subscribing to my YouTube channel. I will be coming up with loads of video related to your board exam. Till then, stay safe. We will meet again in the next video. Thank you.